So let's make a start. Right, so the things we're going to cover in this session, we're going to look at how to manipulate logs and exponentials. So functions, equations, and identities. We're going to then look at the graphs. So kind of stemming on from what we did earlier, log graphs and exponential graphs, how to sketch them and so on. Then we're going to look at the exponential process, so how to reduce to linear form, and also exponential growth and decay. So let's have a little look. Right. So to start with the manipulating exponentials and logs, let's have a little look. So hopefully we've all met this at least once, but we're going to go right from the start. Again, all exam boards will cover this. Now, exponential functions contain a variable x in the exponent. So unlike polynomials, it's not like x squared or x cubed. It's something to the power of x. So the variable is actually in the power. Okay, so that's a big difference to what we're used to. So, for example, in general terms, if we had f of x equals a to the x, the variable is in the power. That's the function. So this bit, if I just color code this would be the exponent. A would be the base, and this would just be a number. And so that's the general setup. Now, e to the x is a very specific one. E is Euler's number, and it's actually a very specific and special case to look at. So e, if I just make a note here. So this number here, you might have seen it on your calculator. A little bit like pi, it's an irrational number, and it's like equal to 2.718, and then just sort of infinitely changes. So it's this number, we can't express it as a fraction, and so we choose to express it symbolically like we do with pi. So in maths, when we can't express something as a fraction, it's known as irrational, and therefore we have to introduce symbolic notation. So for example, give it a Greek letter, pi, call it e, or use root 2, right? Use the actual surd symbol, for example. So e to the x is a really special base to use, e, because actually it's the very specific example where if you take e to the x, this is kind of mind-blowing for those that have done lots of differentiation. This is such a rare situation. When you differentiate it, does anyone know what happens? Hopefully this is such a classic case that the derivative is itself. So this is like a bit like what's going on here. When you differentiate a function, you get quite a different function as the derivative. For example, x squared will become 2x, cubics will become quadratics, and so on. Exponentials differentiate to make exponentials, and this specific type literally becomes itself. So its derivative is doing itself. Its derivative is doing the function. So basically what that effectively tells us is the y value at a point is the same as the steepness at that point. Its derivative is exactly the same as its output. Its gradient is changing in the same way the function itself is changing, which is a really unique property. And so if we took that a step further, d2y dx squared would still be e to the x. Okay, so this is almost like the most perfect scenario of exponentials because its derivative is itself. And those of you that have seen, we can take this further, is that if it's not just e to the x, it's e to a function of x, like kx, the derivative of that comes down. So e to the 5x would differentiate to 5e to the 5x. And that ties in with something you do in year 13 called the chain rule. Okay, right, let's keep going. So that's a kind of introduction, but we've probably seen that. Now, what we've also got to look at is the idea of inverse functions. So the logarithmic function log base a of x is the function that undoes the exponential. So what we mean by inverse functions, and we do need to be clear on notation as well. For example, if you have f of x is x squared, then that would tell us that the inverse is root x, the function that undoes it, almost like the inverse operation, but the inverse function. Because if we have 4 squared, 16, 16 square rooted is 4. It's the reverse process. Likewise, if the function was 10 to the x, the inverse function would be log base 10 of x. Now, some of the older calculators, they just write log, and they mean log base 10, or LG for the really old textbooks and really old calculators. That means that they would conventionally mean log base 10. Okay, and that would be the thing that undoes that. So the example here would be if we had 10 squared is 100, then log base 10 of 100 would give us 2. Tells you the power. It undoes it. Okay, so basically this is something we didn't generally do at GCSE, but it helps us answer the following question. So the logarithmic function, log base a of x, asks the question a to the power of what equals x. That's what it helps us solve. So it's even better than like square rooting or cube rooting if we don't know what root it is. It's basically this to the what equals this. What power of a gives me the thing I want? That's what it's answering. Okay. And then off the back of that, the natural logarithm, ln x, that is basically log base e. So that's worth remembering. So if you've seen that notation before, hopefully you have, that's a very specific inverse function. So AKA ln x is actually log base e of x. It's just, it qualifies for its own notation because it's so particular and special. It's the one that undoes e to the x. Okay, so hopefully that's a bit of a recap for most of you, but let's have a look at an exam question now. I'll give you a few minutes to try it. I really appreciate you all joining, being back promptly and stuff. And hopefully this will be useful. So let me just give you this question here. So 3 marks, and it's to the right, we have a segment of the graph y equals log base 2 of ax plus b. Given that the graph passes through the origin, as well as the point 1, 3, deduce the values of a and b. 3 marks. Okay, so we've got a few things going on here. We've got 3 marks, so 1 for each bit. A method might not be clear, but the problem shouldn't take too long. So we kind of need to piece information together. So to deduce the value of a and b, we're looking for some sort of link. We're looking, what can we do? What can we sub in? We've got this, and we've got this very specific bit of information. Don't forget, they have told us 2 points, and we can see them on here. So if you think about it, there's 2 unknowns, and there's also 2 potential equations we could form. Right, I'll give you a minute. Let's see how we go, and then I'll push this on. Very good. Hopefully we can make a start to this now. Do feel free to keep the questions coming in. Well done. Right, so about 30 seconds, and then we'll see if anyone's got it. That would be great. Great to see that. And we'll push through and work through this question together, look at how the marks are allocated and so on. That would be great. Okay. Right, let's have a little look. So to use the information about the origin, we know the origin, we've got two values. We've got x and y as 0. 0, 0 is the coordinate. So if we sub that information in and then begin to solve, x is 0, y is 0. If we sub that into the information there, we get 0 equals log base 2 of 0 plus b. So log base 2 of b is 0. Okay, so well done if you got that. That's like almost forming our two simultaneous situations. Right. Deduce the value of b. We've also got, we can undo that to actually solve for b. So your first mark is going to come from this. Now, if we know log base 2 of b is 0, remember this tells us this to the power of this equals this. I'm saying 2 to the power of what gives me 2 to the power of 0 gives me b. So b must therefore be 1. There's your first mark. Hopefully that's okay for everyone. Just check that's all good and let us know if not. And then for the second bit of information, we're going to sub the other coordinate in, given that we now know what b is. So we now know that b is 1. We may as well replace that in there because there's one less unknown. So we're going to sub x in as 1, y in as 3, and b we know is 1. So we're just looking for a now. So sub x and y in as those values. 3 equals log base 2 of a times 1 plus 1. And then we're going to solve this. So this is where we're at. And we've got to be careful here. So we're going to raise 2 to the power of 3, which is 8. 2 cubed is 8. And this is the kind of key idea we're looking at. This to the this is this. So 2 to the 3 is 8. And hopefully that's clear for everyone. So now we know that 8 is equal to a plus 1. We can solve for a, take 1 away from both sides. A is 7. So I'll just leave that there for a minute. So they're your two final marks. And that's just walking through it, finding a, putting the other point in by putting the value for b in, and then you've got a and b. Brilliant. Right, we're going to keep going. Now, just going through a few of the key rules for logs and exponentials. Let's have a little look. So, exponentials and logarithms, we can basically manipulate any expressions involving logs and exponentials, but particularly logs using the log rules. So these, again, many of you will have learned, and you might have just learned them off by heart, but they do come from the idea of reversing what we would do with powers. If you think about when we times powers, we add the exponents. So an addition of logarithms, which represent those exponents, actually reflect a multiplication of numbers. So this is where these rules come from. So just to give you a few little examples to the side, for example, we had ln log base e of 4 plus ln 8. Hopefully we're happy that just using this rule, that would be equivalent to ln of 32. Yeah, because the addition becomes a multiplication in the log. Cool. Right, the division one, this one here, ln, let's say, for example, 24 minus ln 8. That would be ln 3, because it's not subtraction, it's division. Brilliant. And this one, this is the one that, for some people, it looks the hardest, but it's the one I've noticed students probably recall this one the best, because you're kind of paying attention to it. So, for example, the power comes down and comes out of the log. And you can kind of explain the logic behind this using this. If it's log ax plus x, that's like x squared, because it's x times x. So the power is the collection of how many of them you have added up. So effectively, if we had log of 16, you could equivalently write that as 2 log 4. And it's noticing little tricks like this that are really useful. If you can write it as a power of something else, you can often simplify the logarithm. Brilliant. Right, let's keep going. We're going to look at a few more rules and then do some more harder questions. Here we go. So we can use laws of logs to solve equations of this form. So the form a to the px plus q equals b. So basically what we need to do is choose the log of base a. So we're going to choose, let's have a little look. A to start with, in order to simplify the problem. So for example, we would take log base a of, what was it, a to the px plus q. So because it's an equation, you have to do that of both sides. Log base a of b. Hopefully we're all following up to there. And some people do sort of almost skip right in this step, but I think it's really important. Then we're going to apply the power rule. So this can come down the front. And we'd get px plus q, lots of log base a of a. And now log base a of a is actually 1. Because if you think about it, log base a of a, we're saying a to the power of what is a? 1. That's the only situation where that will work. So, and also you might just think, well, yeah, I know that would happen because the point of taking log base a was to cancel out the the exponential situation. So yeah, very good if you followed that. So now we're at this nice stage where we've got basically px plus q equals 1. Sorry, px plus q, we've got times 1 equals log a of b. And our aim is to make x the subject. So although this might not be nice, this will just be a number when you sub a and b in, or you rearrange, if we were doing it numerically, and then you get the final answer. So basically make x the subject. So x equals log a of b minus q over p. Now we did this algebraically, but if you had numbers to sub in, you would find the answer using your calculator. So that's just the general setup of how you'd approach this question. And we're going to practice it directly now. So here we go. Here's one, perfectly modeling this thing we've got. So 3 steps, hopefully. We've got the answer in there as well as part of the marks. X is an index. We'll need to bring it down. So we need laws of logs. We'll need a calculator at the end because it says to 3 significant figures. And that's good. So I think, again, let's give this a go. I'll give you a minute head start and then we'll go through it. Brilliant. Here we go. And if you're actually still really confident with all of these questions, that's great because obviously pure maths will be 2/3 of your course. So we want to be really strong at pure, but we want to be also quick for time and also anticipate the problems with the questions. What's going to slow us down? Where are the trip hazards? So we'll go through this again together, but give it a go yourself. Follow those processes we just did. Remember how you undo e to the something. It's got its own very special function, inverse function. Use a calculator by all means, and we'll check this shortly. Okay, right, let's begin to go through it. So hopefully I'm giving you enough time to have a head start, but we are pushing on at a bit of a pace. So e to the 2x plus 1 equals 2. First thing we're going to do is take logarithms of both sides, specifically log base e, which we call ln of x, ln. We denote it as that. Now the ln of x undoes the e to the power, and it just brings down 2x plus 1. So if we tidy that up, we get this, and ln of e is 1. So we basically get 2x plus 1 equals ln 2. Very well done if you're at that stage. We're already picking up the key marks. Right. So moving this on, because hopefully that's very much the same step as before, but instead of log base a, we're using log base e, which is ln. So here we are. 2x plus 1 equals ln 2. The aim is to find x, so we're making x the subject. So very simply, we're going to minus 1 across, and just be very careful with this, that the minus 1 goes on the outside. It doesn't go in the log. But hopefully that's a mistake you wouldn't have made, just to look out for though. So ln 2 minus 1 all divided by 2. Hopefully that's the answer you get. Now, don't forget, guys, when you've done this on your calculator, for exam confidence, check it, put the answer back in the original question so you can move on confidently. So if you take your answer A and S button and you go e to the 2 answer plus 1, hopefully it will spit out 2, and then you know you've done it right. And that's how you can maximize marks as well. But not just maximize marks, maximize confidence. Any algebra, any trig, any exponentials, any equations that you're solving, try to check they actually work, because then you know how much of the paper you've actually worked out and it's correct. And you can move on to the other parts of the question really confidently. Right, brilliant. So to free SF as well, pay attention to that. So let's look at exponential and logarithmic identities. So an identity is something that's always true, because these will help us simplifying problems. So because a to the 1 is a, this is therefore true. Because a to the 0 is 1, this is always true. So we can kind of use this as a given. And then this one, this sort of stems from something else we've just seen, which is we know that log a of 1 over x is like x to the minus 1. And by the power law, that can come out the front. This is a really handy one to know, this rule here, because that's especially when they ask you to manipulate the answers in a particular way. And then finally, this is the one that catches people off guard. And when we see this a couple of times in year 13, when we're doing differentiation, how to show certain things, it's almost like overkill with this. A to the log a of x is just x. It's like saying sine of inverse sine of x is just x. A function and its inverse undo each other. X squared square rooted is x. That's basically what that's doing. So it undoes itself. Okay, let's keep going. We're doing really well. So I think we've got 2 brilliant questions to look at now. We're going to push on with. Again, so these are a little bit bigger, a little bit trickier to deal with. I'm going to give you some thinking time again. But it does say your values of both y and x should not be written in terms of logarithms. So it's 5 marks. Most of the marks are probably for the second part. We need to rearrange the equation, basically to find x. And it should hopefully resemble a quadratic. Those of you that have done a lot of practice will recognize this as the kind of quadratics in disguise question. First part is probably much simpler, but we've still got to think carefully. And this is really crucial as well, how we present the answer. So give it a go. Again, I think I'll give you a 1.5 minute head start, then I'll start working through it. Really, really well done. So we've gone straight into some more difficult pure content. As I said, this will take us till about 2:15. We'll have a short 15-minute break. and then we're going to hit the applied maths. So we're going to really build up exponentials and logarithms. Right, a minute and a half, I'll be quiet, and then I'll start working through these with you. Okay, right, let's have a little look. So for some people, you might actually think the first one looks worse. But when we start looking at the rules we just used, it's maybe not as bad as it first seems. So let's have a little look. So for the first one, we want to try and simplify it to a single logarithm if possible. So we're going to move stuff to one side. So ln y minus ln of 1 over y equals 1. Well done if you did that first. I think that's an important first step. Now, we've seen that ln of 1 over y is the same as ln of y to the power of minus 1. And so a factor of minus can come out. And because there's already a minus there, the minus minus will become a plus. So we get ln of y plus ln of y. And then basically they times together, ln of y plus ln of y is ln of y squared. And that's equal to 1. And then where we can go from here is if we raise both sides to the power of e, y squared equals e to the 1, because that's how we undo. Oh, I need to swap the pen back. E to the that equals e to the that. They cancel. So y squared equals e to the 1. And just bear in mind that when we square root both sides, y must be greater than 0. So we don't say plus or minus square root for this. Y is greater than 0. Why is that? Well, actually, because it came from a logarithm. And those of you that are clear with log graphs and recognize the domain, you can't put a negative in a log, because in the same way that e to the x has an asymptote at 0, a negative will never come out of that. So you can't do log of a negative number. So y equals root e. Cool. So that was a good first question. Just took a bit of manipulation and then raise it to the power of e, and we're done. So we'll look at the next one now, because this is, if you've practiced this next type, you'll probably know exactly where to go with it, and you'll be quite keen and buzzing to go, yeah, I know how to do this. But that first one can catch us off guard. So here we go. This is our sneaky quadratic question. So this is the kind of question where we need to use like a substitution. We need to, and first of all, we actually need to spot what the substitution is for those of you that do it this way. So if we notice 3 to the 2x and 3 to the x, they're different things, but they are linked. So we know that 3 to the 2x from laws of powers, index laws, can be written as 3 to the x to the 2. So 3 to the x all squared. So that means if we replace that, it looks a bit more like a quadratic now. Hopefully, we've all seen this sort of situation before. It definitely comes up. It's definitely another kind of exam favorite. So you probably have seen this. But it's getting that kind of disguised quadratic written explicitly as that's the squared thing, that's the x thing, and that's the constant term. So Going from there, if we now look at a substitution, we can ignore that it's 3 to the x and we can call it u or y or something else. And if we replace 3 to the x with y, we'd get y squared minus 12y plus 32 equals 0. That looks a lot more familiar to us. So going from here, let's have a little look. Couple of marks already for this question. And hopefully we're all following. I'm hoping this is nice and clear. So do make a note. As I said, at the end of the session, when you fill out the survey and stuff, you'll get all the solutions sent to you after you fill that survey out and you've attended the session. But do just try and follow what we're doing and ask any questions if anything's unclear or if I've missed anything. Great, let's keep going. Now, solving the equation in terms of y, solve the quadratic as you would. This one happens to factorize. So we can deduce that y would equal to 4 or 8. And then solve the equation in terms of 3 to the x. So you can either put it back in that factorized form or actually just say, well, 3 to the x needs to equal 4 or 3 to the x equals 8. And so from there, we can go on to solve the final part of this using logs base 3. So if I know that 3 to the x equals 4 or 3 to the x equals 8, to solve this, there's two little situations to solve. 3 to the log base 3 of 4 or log base 3 of 8. And then it did say don't leave it as a log, so give it to 3 significant figures. And again, check it works. Put those values back in the original problem, and then you know with confidence you've solved it. Brilliant. Right. So that's another type of question you can kind of guarantee or at least move on in the paper knowing you've got it right. Great. Right, let's keep going. Let's look at the graphs. So we're going to spend a little bit of time looking at the graphs, and then we're going to move on to modeling with exponentials and logs. And this does tie in with some of the stuff in the statistics course as well, for those of you that have covered that. So again, knowing the graphs of exponentials and logs is a key thing for all the exam boards. They're all going to be testing this. It's in all of their specifications. Every spec will say e to the x and learn, and any transformations of logs or exponential graphs we kind of need to know. Now, first of all exponential functions are of the form y equals a to the x, have a gradient which is actually proportional to their value. So basically what that means is the derivative for any exponential is related to the function itself, is proportional to a to the x. Okay, and you will explore this a bit more in calculus in year 13 as well, for those of you that haven't already. So functions which increase exponentially grow at a rate which increases exponentially. So that's what we're effectively saying. So if you imagine this is y equals 2 to the x, we can also recognize from graph transformations that if you changed it in the function, you made it minus, that's a reflection in the y-axis. So 2 to the minus x would look like that. And that would represent like depreciation or decreasing exponentially. So some key things, they both go through, or they all go through the coordinate 1, 0, 1, and less transformed. And they kind of get less steep, shallower and shallower, because what's happening for negative x is the power is making it a fraction and the denominator is getting bigger. So it's, the actual value is getting smaller and smaller, tending towards 0. So we have an asymptote. And that's the general sort of shape of what's going on. So the kind of key things to look out for is the curves are steeper for larger values of a. So if we had a comparison there of, say, for example, e to the x, and if this was like y equals 1.5 to the x, that'd be a bit less steep. And then if we did that, that might be something like y equals 6 to the x, because 6 is bigger than e. So they've got a lot of key features they share. They're all pinned in position at 0, 1, because of course anything to the 0, the x ordinate, will equal to 1, which is the y-ordinate. So 0, 1 will always be a coordinate pair that satisfy all of these. And also they'll all tend towards the x-axis on the left-hand side. So they will have a y-intercept equal to 1 for all values of a. It'll be that one will be a reflection, like we mentioned. And that is effectively because 1 over a to the x is basically the same as, and it's important actually to make that link, but that's what's going on there. And like I said, this does tie in with like compound interest and depreciation and all those situations we've seen before. We've just never really looked at the graphs that carefully when we've seen it at GCSE and so on. So yeah, right, we'll keep going. Again, classic thing of doing a question and seeing how we go. But as we mentioned right at the start of today, the examiners have said how important it's going to be that topics bring together lots of skills. Even in the coordinate geometry session, we saw derivatives were used, completing the square was used, knowledge of tangents, knowledge of graphs. We've also seen graph transformations come up again and again, lots of similar rearranging techniques. So here we're asked the following plots we've been given for 2 to the x. It says on the same axes, add sketches for the curves y equals 3 to the x and y equals half to the power of x. So 2 quick parts, 2 minutes you'd probably have in the exam. It shouldn't take too long. It's just kind of getting the key ideas and sketching it on that same graph axes so that it has the right shape. So I'm going to give you maybe 30 seconds and then I'll project up the answers. Let's give this a go and keep things moving. This is really, really good. And then we'll look at log graphs, and then we're going to do a little bit more modeling with logs and exponentials before taking a short break. And then we've got a very full-on afternoon of applied content, which I hope is going to be really useful to everyone. Right, cool. So quick check of this. So if we've got the graph of 2 to the x, then simply put 3 to the x should be steeper. So we know the conditions that should be the same, should intersect the axes, same intercept. It should be steeper. And this is what's going to get you the marks. It almost seems really straightforward that that's all they're looking for. It's not got to be like a computer. You're not going to be like a robot, how you've sketched it. It just needs to be accurate in that it's steeper, it shares the common features, and it's a similar shape with the correct same asymptote. And that'll get you the mark. Nice, 1 mark in the bag. There we go. So then the next one, for the inverse graph, 1/2 x. Now think about 2 to the x. A half is like 2 to the minus x. So 2 to the minus x is a reflection in the y-axis, as we mentioned earlier. So that will be it, another 1 mark. And it's almost like one of those all or nothing things. You either know it or you don't. Right, let's look at log graphs. So logarithmic graphs, you do need to know how these look. You do need to be able to sketch them. And it's actually not that complicated. If you know what an exponential looks like, you can very quickly learn what a logarithmic graph looks like. So basically, logarithmic functions cross the x-axis at 1, 0, and they have the y-axis as the asymptote. So basically, and those of you in year 13 that have done a bit more functions, if you've done inverse functions, you will recognize that a graph and its inverse are reflections of each other in the line y equals x. So if you know what e to the x looks like, then you can just reflect that and you know what ln of x looks like. Okay. And again, we know that ln of 1 is 0. So that sort of tells us why there's the x-intercept there. So notice that log graphs don't exist for negative numbers. Log functions don't exist for a negative domain. So this graph is sort of bounded by the y-axis. That's the asymptote. But if you think of it or you appreciate it as a reflection of e to the x in the line y equals x, that can really help you sketch it. And I hope that is a good way of remembering it, because some people really make a meal of it and think, oh, I don't know, it's another graph to learn. I'm not even really sure I understand logarithms. How can I know what the graph looks like? It's absolutely fine. If you know the shape of an exponential, then you know the shape of a logarithmic graph. Brilliant. Right. So let's push on. Oh, one point actually as well, based on what I just said, some people think there's like another asymptote here, which there isn't. If you think about an exponential, there's not an asymptote there. So the only asymptote is the y-axis. This is just getting bigger and bigger forever. Okay, so that is a key point. Right. So I've kind of jumped ahead here, but we've already sort of mentioned this. It is a reflection in the line y equals x. Okay, so if f of x is e to the x, and f inverse of x would therefore be ln x, then they would be the mirror image of each other if the mirror was the line y equals x. Okay, and again, same with those points, 0, 1, and 1, 0 would reflect across. Brilliant. Okay, so I'm hoping that's all nice and clear. Right, again, we'll do an exam question, and then we're going to move on to the modeling part. So this will be a really good little bit of consolidation. Then we're going to get onto the modeling part, which does sometimes tie in with statistics. And then we'll take a break after that. So here's your question, 2 marks, 2 quick, simple parts. Again, 1 mark for each bit. So what we've got is we've got a curve that they're related to one given function, and you're given ln x drawn out. Again, should hopefully be straightforward as long as we've practiced and we've seen what these graphs look like. So I'm going to give you again 30 seconds, make a start, quick sketch of it if you can, and then we'll check it. And as I said, it's bringing all these skills together: graph transformation, sketching, logs, exponentials. Yeah, cool. So 20 seconds or so. Okay. So let's have a little look. Brilliant. And guys, I do just want to say thank you so much as well. I know I appreciate how much time you're giving up. And this is a full-on day of so far just pure content. We're going to get on to the applied. But really well done for committing the time to practicing these kind of questions, especially when it's stuff that's new. We can often dodge the bits we like or the bits we don't want to do. And you kind of have to attack all of it for this A-level. So let's have a little look. E to the x is the inverse of ln x. So therefore, there's your sketch straight away. And we've literally just been through that. So it's just a sketch, get the shape right, get the key points right. There's your mark. Next one, ln x plus 2 is a transformation, isn't it? It's happening inside the function. And so we do the opposite to x. So we're going to -2. So we're going to move this graph to the left by 2. And so now what we'll see is it will look like this. And so this situation, we've moved the graph across. And likewise, the asymptote will have moved across to x equals -2. So it's the same shape translated across. Okay, very well done if you got that. Now, another point I do just want to stress is because they do often say intersections with the axes. Now, we know that that went through 1, 0. So moving that 2 across was easy. This point is really important that we find as well. Remember, this is when x is 0. So if it's y equals ln x plus 2, and we put x in as 0, y equals ln 2 is the y-intercept. Okay, so just always remember for any graph, you can find x-intercepts by putting y as 0 and solving, and you find the y-intercept by putting x in as 0, because you know half the coordinate already. Right, let's keep going. So we're now looking at exponential processes, and this is the bit that I think the reduction to linear form with the modeling that is very new. It's certainly been added since I did the A-level. So quite a big change, but useful and very much for the purpose of actually modeling maths in a real context. So let's look at this. Again, all exam boards are going to now focus on this in their exam. It's kind of a national change that all exam boards had to sort of recognize and incorporate into their A-level. So what we've got is if we have x and y have an exponential relationship, so ab to the power of x, of course, we can use a table of values for x and y and start like plotting it and stuff. But what we can do is we can also convert it into a linear form. So we know that an ab to the x is that sort of shape, but we can reduce this to a linear model. And the way to do this is to deal with it like logarithmically. So if I take log of both sides, say log base 10, I would get log y equals log ab to the x. Now, I would say this is a really important set of steps we're going through. And it's the same process with the two types of questions I'm about to do. That people get all in a big sort of mess about this, and they think they have to learn loads off by heart. First thing you're going to do is take logs of both sides. And that's what we're going to practice doing here. So take logs of both sides. And I can actually tidy this up, can't I? Because I know log rules. So I could actually say that log y is equal to, check you agree, log a plus x log b. And now we're in a kind of simpler form. Now, if we compare this to our straight line equation, y equals mx plus c, let's make a little kind of comparison. Instead of y, we have log y. Instead of mx, we have log b lots of x. And instead of c, we have log a. Okay, so I'm going to do this now with arrows so that we can, but this is literally a matching up process. So log y is like our y, log a is like our plus c, and the log b is like our m, because it's the bit that goes with x. So what this means is if we were to, instead of use x and y, work out some log data, like put y into log base 10, we could actually plot a different graph that would be a straight line that would encode all the same information. And what we've just found by matching it up, and if I just try and stick with a color code in here, is that the gradient m, that we'd normally call m, would actually be equal to what? It would be equal to log b. And the y-intercept, which we'd normally call c, will actually be log a. Okay, so let's have a little look. We're good to carry on. Hopefully that's all good. And this process is very similar in another situation we're going to see in a minute, but I want to work us through a good, clear example of this before we practice a question of this type. So here we go. So for example, if we have the original x and y values, the data there, what we can look to do is we can actually go, well, I can find log y, log base 10 of y, and I can put those in my calculator. So I found another set of variables, log base 10 of y, that directly relate to y, literally from my calculator. Are we all good with that? Just literally log base 10 of y, do that for all the y values. Now, if you plot the x values, against the log base 10 of y values, what we would find is we would have a linear relationship. If one of them is out, then you check that because you probably made a mistake. But you should notice they all lie on a straight line. And so what we have here is this, instead of the x and y axis, we have the x and the log base 10 of y axis, which still obviously relates to the x and y variables, but it's now a straight line where some of that information is kind of encoded in a sort of secret way. So we just discovered a minute ago that the gradient was actually, what was it? It was log base b, log base 10 of b, and the y-intercept was log a. So now bringing this all together, let's look at what we've got. So we said that in the straight line form, I'm going to write this out nice and carefully, log base 10 of y is equal to I'm going to really try and do this neatly and color-codedly, in a color-coded way. This was the thing we got right at the start. Now, if we match that to this graph and see what we can find, a really nice thing to start with is, now obviously this is really hard to read off on this axis, but if you had a much nicer graph, I'm going to help you out. This is 0.698. If I just told you, if we zoomed in, if that was really done precisely. So I'm going to tell you that. And then I'm going to tell you, let's look at the gradient. So I'm going to pick two easy points. And I'm going to say like this one. And probably the one up there. Okay. And then what I have is the change in x is it's gone across by 3. And the change in y is it's gone across by 0.9. So I can also work the gradient out, change of y over change of x. Yeah. And then match it to these corresponding features. So if I deal with the gradient first, log base 10 of b, and like I said, I think this is crucial for us to go through. So when you first go through it, it feels really tedious. It's actually fine. It's fine as a process. It just is practice. This must be equal to the gradient m, which we know is change of y over change of x. So basically 0.9 over 3. But to help me find b, because b is the thing I care about, then that means that 10 to the whatever that is, 0.3, equals b. So 10 to the 0.3 equals b, which is approximately 2. You can look it up, see if you get it more exact, but I think with 3 significant figures is good enough. Now, to find the C bit, we're actually looking for A ultimately. We know the y-intercept is 0.698, and that was equivalent to log base 10 of A. So that's just another little one to rearrange and solve. So 10 to the 0.698 must equal A. So A, that would be equal to, approximately equal to 5. Okay. So what that means for this graph is like, what was the point of all of this? Why were we doing all of this? Well, ultimately, we wanted to find A and B, find what the original exponential was from its data, from the values that we knew were connected in an exponential fashion. We want to actually find the original values for the graph. So now putting that back in, that means this was y equals 5 times 2 to the power of x. Okay, 5 and 2 might have been slightly rounded for this example, but we could have given them to more decimal places if we wanted. That's what we found. So we've quite powerfully found the original exponential constants and values and base numbers from points on their exponential graphs. We've reduced it to a linear form. We've worked out the gradient and y-intercept, and we've interpreted what they mean in the context of the original model. So that's a really massive skill and a real big thing to add to the A level. So you can imagine that this is a really good type of question to practice. Okay. And also embedded in there, you need to be good at dealing with taking logs and solving exponential and log equations. So what we'll do another little example, and then we'll do an exam question together. So I think that'll be really useful. So let's have a little look. Now, this is the one other type of question they can get you to do this process. And I know that when I've taught this to classes before, they get very overwhelmed and they're like, oh, I've got to learn a whole other thing as well. It's basically the same. It's basically the same method, but we've just got to match different bits. So the first step is what? It's to take logs again. So let's start by taking log base 10 of both sides. First thing I'm going to do, log base 10 of y equals log, and I'm just going to write log for now, shorthand for log base 10, equals log p x to the n. And notice that this is a different type of equation. I maybe didn't stress this a minute ago. The last type, where it was ab to the x, was an exponential. This type, where it's px to the n, is more like a polynomial. It's more like an x to the power, like the kind of graphs we're more familiar with. Although obviously p and n might not be whole numbers, this is not an exponential graph this time. This is an anything power of x. So x is now the base, the variable is now the base, but we're still going to use the same process to reduce anything like this to linear form. So what we can do is we can tidy this up a bit further, just like we did with the last question. And we're going to get log, getting too excited here. I'm going to get this done nicely. Log p plus log x to the n, or n log x. Let's all check we're happy there. I'm going to just pause that for a moment. Okay, hopefully we're all good. Now, we took logs of both sides. Now we're going to do that same thing where we compare it to the straight line. So log y is like our y. Log p is like our little constant. And this time it's a little bit weird. mx is n log x. So this time, instead of x, we have log x. And n is our gradient. So the difference here, last time we had the log y values. This time we need the log x and the log y values, so that we can graph them. Instead of x against y, we're going to use log x and log y. Okay, so what we would have this time, in a very similar way to before, is the gradient would be n when you do log x against log y, and the y-intercept log p. Okay. So let's have a little look. Here's a question. Right, brilliant. So we're at this stage already. We're nice and prepared for this. We're going to go through this carefully together. And then, yeah, I think we've got another exam style question to do. Then we'll take a short break before hitting the applied content. Okay, so 4 marks, 4 stages. We need to sort of remove the logs. Let's have a little look. What else are we doing? Yeah, so we need to kind of expect it to be of that form. So we're kind of anticipating this the other way around. And there's the graph. So if you've got that in front of you, if you want to have a little look at that, let's just reread the question and then I'll let you give this a go. So the graph has the relationship of log 10y, log base 10 of x. So we know that this isn't a log y against x. So it's not an exponential. This is a px to the n one that we've just looked at. So that's what we should be looking out for. And again, we know the key things to try and read off are the gradient and the y-intercept. So I'm going to let you have a look at that and see where we can go with this, matching it up, and then I'll walk it through. Then we'll do a big exam question before taking a short break. Okay, right. Give you a minute head start again, and then start going through it. Okay, right. Let's start having a look together. So the change in y, 0.4. And the change in x, I believe, is 0.1. So let's see what we've got from this. Y-intercept is 0.3. So shape of the graph, because it's log base 10 of y and log base 10 of x, it was of that form. So if we looked at the gradient, which we did, 0.4 over 0.1 is 4, and the y-intercept was 0.3. So if we match this back to that information in that format there, remember undoing that in the way we did, then what we had was initially, this would be the same as log 10 of x to the 4 and log 10 of 10 to this value. And so putting it back in the original form, combining it all up, or just making a match up to what we originally did in the example before, we then know that 10 to the 0.3, which you can simplify to the nearest whole number as 2, and x to the 4. That's what it came from. So unlike the previous example, which was exponential data, and we had x against log y, this was log x against log y, so this was a something x to the power. And by putting in the y-intercept and the gradient and then undoing that process, or just matching it up, if you were to use the slides from earlier where we said about this, we could have worked out the original p and the original n. But it sometimes helps to just go through that process of taking logs and then going backwards. So hopefully that was a good example to go through. What I do want to do now is take this one final step further before taking a break and then do a big exam question of this together, which we'll actually just work through fully together. So exponential growth and decay, this is where it's really going into the modeling side, where it will be an actual context. So it could be to do with population, it could be to do with money. You can imagine there's loads of different scenarios they can dress this up with. So what we've got is many real life processes can be modeled as exponential functions, as the rate of increase is proportional to their size. So it's growing in that proportionate way. So for example, compound interest has this shape where we've got a multiplier like 1.1 to the power of whatever, as you've probably seen at GCSE. And hopefully that's actually a very familiar formula almost. You might have written it slightly different at GCSE, but T was, remember, like often the time in years. And then this is like your decimal multiplier and so on. So that becomes, in this case, your exponential base. And the time is the exponent. So if we think for this, A equals the amount, P equals the principal value at the initial amount, T is obviously the time, and R is the interest rate. Let's look at what's going on. So if P goes through at $1,000, that's obviously what we started with at time 0. So P equals to 1,000. Okay, and then say, for example, like R equals 8%. Then let's have a little look at what we would have. So that graph could be showing something like that, how the money increases with an investment and so on. Now, in a similar way, you could have decay or depreciation, like radioactive decay here. But similar sort of thing. What we've got going on with this situation is N for this, for example, might be the number of atoms. Again, T is often time. Number of atoms. T equals time. And then we've got like this factor lambda as well, which might be like a decay constant. So let's have a little look. Hopefully that's all clear. Brilliant. So for example, here, what we do know is the y-intercept or the n-intercept would be 8,000. You'd also have, and the way you could check that is if you put t in as 0 and you did 8,000 equals, sorry, if we were actually to put in t as 0, that would all go to 0 and n would just be 8,000. So that's how we know that's the y-intercept. Bit like putting x in as 0, we're putting t in as 0. Brilliant. So we're just going to do this exam question quickly and then have a short break. So we're going to keep pushing on for now. So what we'd say is, yeah, that was that example, and that can allow us to find the y-intercept for the initial amount very quickly. So here we go. Let's do this example together, and then we'll take a short break before doing the applied. So the Mayor of London has determined the need to track the city's pigeon population. So in 2012, there were an estimated 1 million pigeons in London, while in 2018, there are an estimated 1 billion pigeons in London. So a model of the form n, capital N, equals ne to the kt is suggested, with t as the number of years since 2012, k as a constant. Use the given data to calculate suitable values for n and k. Give your answer to k to 3 significant figures. Right, lots going on here. So it's a real world problem. So this is telling us that we do need to sort of answer it in context. 3 steps expected, 3 marks. 2 values required, so we need to do a simultaneous equation, and one of them eliminated for t. So we need to round. That's what it's telling us as well. It's probably going to be a nasty answer. So we're going to give this a go. Right, so the information that we're given. So the initial value we're told is 1 million. The second value we're told is 1 billion. The time that's passed is 6 years. So we can lay that all out. So setting this stuff out will help us sort of set up the question. And we know we're dealing with a model like this. Right, so let's look at the known data. When t is 0, the initial value of n is 1 million. So we know that this is a case we have. We've done a very similar question to this earlier, where we plug x and y in and x and y in and find a and b. Right, I'm plugging t in as 0, and I know the population's 1 million. So that's what I have. So e to the 0 is 1. So n must be 1 million. That must be where it goes through the y-axis. Great. So we've already refined the model. Now, use another known value that we have. Well, we know that 6 years later, there's a billion in the population. So I'm going to put that value in. So I know that a billion equals a million times e to the 6k, and I can solve this. So divide both sides by a million, and 1,000 must be e to the 6k. I can solve that. I can take logs of both sides. So take ln of both sides, and ln of 1,000 is 6k. Divide it by 6, and I've got k. And do notice it did ask us to round it in a specific way. So that's it.